We tend to think of the internet as an invisible, weightless resource floating somewhere in the cloud. But the reality is that the web is a massive, heavy physical infrastructure. Keeping the internet online requires millions of physical servers sitting in massive data centers globally. Those servers burn an enormous amount of fossil fuels to operate, and they require an aggressive, constant supply of electricity just to power the cooling systems that keep them from overheating. A major reason for this energy drain is how we design the web itself. We build digital spaces the same way we build industrial factories. We construct static, rigid blueprints that force every single visitor to load the exact same heavy structural framework, regardless of what they came to do. This animated diagram shows how a traditional server filing system handles data over time. Notice these red blocks piling up. That represents content bloat, the years of outdated, unread data that websites hoard and permanently lock into active servers. Treating our digital infrastructure like an endless industrial machine is directly responsible for a massive, rapidly expanding digital carbon footprint. The sheer weight of the web is unsustainable. To fix it, we have to ask what would happen if we stopped constructing the internet like a rigid machine and started cultivating it like a living organism. On the left, you see biophilic design. That's using nature for aesthetic decoration, like putting a calming picture of a leaf on a homepage. But the image on the right is biomimetic design. This is the practice of stealing nature's functional logic to solve complex engineering problems. We already do this in the physical world. Engineers redesigned the Japanese bullet train to mimic the aerodynamic beak of a kingfisher so it could enter tunnels without creating sonic booms. Architects have built self-regulating passive cooling systems modeled entirely on the airflow of termite mounds. Nature has spent 3.8 billion years conducting evolutionary research and development to figure out how to optimize resources. Applying those tested strategies to our digital infrastructure represents a shift from building for infinite growth towards designing for circular, resource-tight systems. Think about the flaw of the traditional static web grid. When you click on a site, the server forces your device to download the exact same dense, heavy architecture as everyone else, even if you only need a fraction of that information. To fix this, developers are building generative AI interfaces. Watch this standard layout dissolve and organically regrow. Operating on algorithmic rules, it adapts in real time based on your profile, pulling only necessary components. Unnecessary background data drops away, drastically reducing server data transfer. Allowing an interface to dynamically grow rather than forcing it to remain static creates a hyper-personalized user experience that simultaneously slashes the energy required to deliver it. We also waste energy on how we navigate these sites. We inherited the filing cabinet method of information architecture. We organize data into rigid folders and subfolders, which forces users down frustrating top-down pathways where valuable content often gets buried. This microscopic view shows a vastly superior biological alternative, a mycelial network. It's the underground fungal system connecting entire forests into a wood-wide web. It is a decentralized, highly efficient network that rapidly bridges gaps between isolated nodes to share resources exactly where they're needed. Ecosystem-inspired websites structure their data the exact same way. Instead of trapping a piece of information inside one isolated folder, it gets linked organically to dozens of other concepts based on context and semantic relationships. By providing users with direct contextual paths to information, we eliminate navigation churn, the energy-intensive process of loading multiple intermediate pages just to find a dead end. When users find what they need in fewer clicks, the total data transfer per session drops, reducing the cumulative energy load on the server. But the biggest drain on the internet is that digital landfill of content bloat we talked about earlier. Millions of web pages that haven't been visited in a decade are still sitting on servers, pulling a constant stream of electricity just to stay cool. In a natural ecosystem, waste simply does not exist. It's a closed-loop system where every output, like a fallen leaf, becomes the input for the next cycle of growth. Through digital composting, stagnant document files automatically break down into basic particles. By identifying long dormant content and actively pruning this digital garden, the material is archived or deleted. As this clutter is absorbed back, the server's workload drops, and the physical hardware actually cools down. Actively composting the web stops the endless accumulation of dead data. It turns our digital infrastructure from a permanent graveyard into a regenerative ecosystem. The most compelling part of biomimetic design is how ecological efficiency and user experience start to converge. When a developer prioritizes lean, efficient data transfers to save energy, they are simultaneously creating the lightning-fast, responsive environment that defines a premium digital experience. Using system-native fonts and pruned datasets means websites load almost instantly. That speed keeps the user engaged while reducing the total number of watts consumed for every page view. And the tools to do this are already online. Machine learning algorithms can process the data required to map out those complex semantic connections, while new code formats like WebAssembly allow standard browsers to run these natural simulations with near-native performance. To lower the environmental cost of our technology, we are moving away from seeing the web as a machine we build. Instead, we are looking at a field, a forest, or a cell, and learning how to cultivate a living, breathing ecosystem.